All right, welcome back. Good day, everyone. Welcome back to our class again. We would like to talk about circular motion today. Now, circular motion is simply the motion of an object in a circle. So here we are just going to be deriving a few equations about circular motion. Good. Let us consider a body. Let's say a body starts from a point. So if I draw a circle, you know that every distance from the center to the circumference is the radius, right? So let us consider that a body moves from a point X and then covers a certain distance, let's say Y. Okay, it is doing so with an angle theta, and this here is the distance S. Okay, so R, let's label the terms or define the terms. R is the radius, S is what we call the arc distance, and then this theta is called what? The angular displacement. The angular displacement. Now, from the diagram, you can realize that the angular displacement is mostly an angle, and therefore it is measured in degrees. Okay, so if an object starts from here and it goes or covers one full cycle, then we say that it has covered 360 degrees. 360 degrees is also equal to one revolution, meaning that it has gone through and revolved once, which is also equal to what we call 2 pi radian. So here our pi is classified as 180 degrees. As we move on, I'm going to explain certain things to you. Now, if I write, let's say pi sine pi, if I write pi sine pi, you realize that this pi is coming after or before sine, and then it is coming again after pi. Now, anytime pi comes before a sign, either sine or cos or tan, then the value is 3.142. But when pi comes after this, then it becomes 180 degrees. Okay, so in most of our calculations, we are going to be meeting pi, and that pi is going to be 3.142 or 22/7, except when our pi comes after sine, cos, or tan, then the pi is going to be equal to 180 degrees. Okay, so this is our angular displacement. In some, the unit for angular displacement that we use most of the times is radian. Wherever or however, when you are given in degrees Celsius, you have to know how to change it to radians or revolution. When you are given in revolution also, you have to know how to change it to radians. So let me just give a few questions or just one question on how. So example, change, let's say 90 degrees to radian. Change 90 degrees to radian. In our solution, we know that 360 degrees is equal to 2 pi radian. Therefore, 90 degrees is equal to x. So x becomes, you know, it's going to be less. So if less, multiply 90 over 360 times 2 pi. This 1, this 4. So you have, let's say, 2 over 4. So you have pi over 2 radian. Okay, so you are changing using simple ratio and proportion. You are changing using simple ratio and proportion. So that is what we can talk about in terms of our angular displacement. Okay, so the angular displacement is simply representing linear displacement as far as motion is concerned. Good. Now, the next thing that we can talk about is what we call the arc distance. The arc distance. From the diagram, you could see that the arc distance is what? S. The arc distance is S. If you look at the diagram once again, you realize that as theta is increasing, okay, as theta is increasing this way, the distance is also increasing. As theta is increasing, the distance is increasing. So our S is directly proportional to the theta, and therefore S is equal to a constant K theta. Now, from the diagram once again, if a body starts from here and then occupies or covers, you see that whilst S is increasing, theta is also increasing. While S is increasing, so if S increases here, the angle also increases this way. The only constant thing is the radius r. Therefore, the k is equal to r radius, implying that our arc distance s is equal to r theta. Okay, so this is what we have as far as the arc distance is concerned, and the SI unit for the distance is meters. Okay, the SI unit for the arc distance is meters. The next thing that we want to talk about is the angular velocity. Angular velocity. You know that velocity is distance over time, or displacement over time. Velocity is displacement over time. And here we can say that the angular velocity, which is omega, is equal to the angular displacement theta all over time. So this is how you go about with your angular velocity. And the SI unit, since this is radian and this is time, the SI unit is radian per second, or sometimes revolution per second. So this is what we can talk about as far as the angular velocity is concerned. The other thing that I want us to talk about is what we call the relationship, or let's just talk about the relationship between the angular velocity and then the linear velocity. That is okay. So the relationship between the angular velocity and linear velocity. So from our equation x is equal to r theta, let's divide 2 by the time t. So you have s over t is equal to r theta all over t. You know, whatever you do here, you have to do here. So I have s over t. But we know that s over t is equal to v. And then also, from this equation, theta over t is also equal to omega. So it implies that from this equation, v will be equal to r omega. So this is the relation or the equation that we have as far as velocity or linear velocity and angular velocity is concerned. As we move on, we can also see, let's just bring about some equations. Omega is also equal to 2 pi f. So the angular velocity is equal to 2 pi f, where f is the frequency. F is the frequency. So sometimes angular velocity is also called angular frequency because of the relation that it has with frequency. Then we can also say f is equal to 1 over t. F is frequency. T here is called the period. And remember, period is capital T and time is small t. Okay, so let's take note of this equation, because as we move on, we are going to apply or use all these equations that we have made. So every equation that I've put in a box is very important as far as our circular motion is concerned. And mind you, physics is a work of equations, and it is very important that we mostly keep the equations that we study, okay, so that all the time we go through our equations and we are okay with that. We move on to another relation briefly. Okay, now the next thing we are moving on, this is one of my favorite equations as far as physics is concerned. A is equal to v squared over r, or A is equal to omega squared r. How do we prove this equation? Now consider an object moving in a circle. Okay, so let's say at this point, as you realize that once an object is moving in a circle, at every point it is changing. Its velocity is what? Changing. But this point, let's say we have a velocity, so we can draw a tangent to this velocity. Let's call this, let's say this point x. So the velocity here is v of x. Okay, this is our radius r. Then the object gets to another point, let's say y here. We can also draw a tangent here. Okay, and then let's call this v of what? Y. Okay, let's assume that the object gets to another point here, let's say z. We can also draw another tangent in this direction, v of what? Z. Good. Now taking or picking any two of them, we can draw a vector out of any two velocities. So let's pick x and then y. So if I pick x and y, this is my direction of x and this is my direction for y. So this is v of x and then v of what? Y. Okay, so this, we can just complete it here. This is our angle theta. We can just complete this so that this is our y, and then this is our x. So let me call this distance x, y. Let me call this distance what? Xy. Okay. Then we know from this diagram that xy is directly proportional to theta. Xy is directly proportional to theta. Let me call this equation 1. Then we also know that acceleration A is equal to change in velocity all over time. We also know that our acceleration A is equal to change in velocity all over what? Time. So let us keep that also. Okay, good. Now from this equation, let me just write A is equal to change in velocity all over the time taken. Let's call this equation 2. From equation 1, you realize that our only constant is the velocity v. Since the change in distance here is given as v of x and we are using v of x, so the velocity is changing as far as the theta is concerned. From equation 1, we can say that xy is equal to v theta, where our xy is equal to change in velocity, because this vector from y to x here is due to the velocity that we have over here. So this is the change in velocity, which is equal to the velocity becoming a constant from the diagram, because it's the velocities that are increasing or decreasing to create the theta that we have here. And therefore, from here to here is our change in velocity. So from here, our constant is velocity. Let me call this equation 3. Okay. Now we know also that our velocity v is equal to, we know also, let me just go back again. We know also that our velocity v here, or our change in velocity, let me just write our change in velocity. We know also that our change in velocity is equal to x, y. So it implies that our equation 3 can be rewritten and our equation 2 can also be rewritten. So our equation 2, so it implies that from equation 2, A is equal to change in velocity all over time, but change in velocity is equal to xy. So A becomes equal to xy all over time. Also, our xy here is equal to v multiplying theta. Therefore, A becomes equal to v theta all over t. This is it. But theta over t is equal to omega, implying that our acceleration A is equal to v multiplying omega. And we all know that v is equal to omega r, and therefore omega is equal to v over r, implying that our acceleration A can be equal to v multiplying v over r, which is equal to v squared over r. Therefore, acceleration A is equal to v squared all over r. This is how we can derive our equation for acceleration. It means that we can also move on to also derive an equation for force. We know that force is equal to mass times acceleration. Therefore, force can be equal to mv squared over r. So for circular motion, we have our force to be equal to mv squared over r. We have acceleration to be equal to v squared over r. We have acceleration A to also be equal to omega squared r from all these equations. Then we can also have the other equations that we have talked about previously. Thank you very much. I'll bring about a question in my next video. Follow my channel, subscribe, and enjoy our class. Thank you. Good day.